So here we are having question number 36. Velocity of most energetic electron emitted from a metallic surface is tripled when the frequency nu of incident radiation is doubled. The work function of metal will be what, given that h is the Planck's constant. Now we know very well that the kinetic energy is what, half mv square. If we triple the speed, kinetic energy will be 9 times. According to Einstein photoelectric effect, the kinetic energy is given as h nu, energy of incident photon, minus of work function phi, equation number 1. If we double the frequency of incident radiation, velocity is tripled here. So that's why kinetic energy will be 9 times. 9 ke will be, frequency is doubled, so 2 h nu minus work function is depend upon the nature of material. Metal surface is not changing, so work function will also not change. So it will remain phi. Solving this equation, equation number 1 and 2, let's multiply with 9 in equation number 1. We get 9 ke equals 9 h nu minus 9 times phi. Subtract them, we get 9 ke minus 9 ke, that is 0. 2 minus 9 h nu minus of 7 h nu plus of 8 phi. After solving, we get the value of work function as 7 h nu divided by 8 as our answer. And after looking at the options, we can say that option number 3 is absolutely correct. We'll go with option number 3. Now let us proceed to the next question, that is question number 37. So here is question number 37. In nth state, the energy of electron in hydrogen atom is En equals minus of 13.6 n square electron volt. The potential energy of electron in first excited state will be what? We know very well that the potential energy of any electron revolving in any nth state is equal 2 times of total energy. Means the electron will have kinetic as well as potential, and the total is sum of kinetic plus potential. So the potential will be 2 times of energy. Now potential we can write 2 into the total energy in nth state, En, given by the equation minus of 13.6 divided by n square electron volt. Now finally we got the expression for potential energy in any nth state. Here it is given that electron is in first excited state. So means for first excited state, n equals 2. Putting value, P equals minus 2 multiplied by 13.6 divided by 2 square, that is 4. After solving, we get the potential energy value as minus of 6.8 electron volt. So finally this is our answer, and after looking at the options, we can say that option number 4 is absolutely correct. Let's move to question number 38. The ratio of maximum to minimum wavelength in Lyman series will be given by what? We know very well that the wavelength of spectral series is 1 by lambda equals rz square in bracket 1 by n1 square minus of 1 by n2 square, where lambda is wavelength, r Rydberg constant, z is the atomic number, n1 and n2 are actually the transition. For Lyman, n1 must be 1. And for maximum wavelength in Lyman series, electron must make transition from second state to first state. So n2 will be given by 2. Plugging the values, we get maximum wavelength 1 by lambda max as rz square 1 minus 1 by 4. We'll get the value of lambda max, therefore 4 divided by 3rz square, equation number 1. Now, for minimum wavelength in Lyman series, electron must make transition from infinite state to ground state. So N2 will be infinite and we get the minimum wavelength 1 by lambda minimum as rz square 1 minus 1 by infinity square. Ultimately you will get rz square and therefore lambda minimum will be 1 upon rz square, equation number 2. We are supposed to calculate the ratio of lambda max with respect to lambda min is given by 4 by 3 rz square all divided by 1 by rz square, and after solving we will get the answer as 4:3. So this is our final answer, 4:3, and we will go with option number 2, which is absolutely correct. Now let us proceed to the next question, that is question number 39. So here is question number 39. When an electron is in 4th excited energy state in hydrogen atom, the possible number of emission spectral lines will be what? Here for 4th excited state, we can write n equals 5, and the relation for number of spectral lines we know very well, n equals n into n minus 1 divided by 2. Put the value of n, that is 5, 5 into 5 minus 1, that is 4 divided by 2, and after solving we will get the total number of spectral lines here is 10. So that's why we'll go with option number 2, which is absolutely correct. Now let us proceed to the next question, that is question number 40. So here is question number 40. In Rutherford experiment, the number of alpha particles scattered through an angle of 60 degree is 20 per minute. Then the number of alpha particles scattered through an angle of 90 per minute by the same nucleus will be what? Now in Rutherford alpha particle scattering experiment, we know that the number of alpha particle is given by the relation n, which is proportional to z square divided by sine to the power 4 times theta by 2 multiplied by e square. Now here it is already mentioned clearly that the nucleus is same, so z will be same, and we can say that n is proportional to 1 upon sine to the power 4 times theta by 2 only. So let's take the ratio for both the cases. In case 1, number of alpha particles, suppose n1. In case 2, number of alpha particles, suppose n2. So ultimately ratio goes something like this. n1 upon n2 will be equal to sine to the power 4 theta 2 by 2, as the relation is of inversely proportional. So that's why something like this, and divided by sine to the power 4 theta 1 divided by 2. Now putting the value of angle, we will get theta 2 is 90 degree, so we will get sine to the power 4 90 by 2, sine to the power 4 60 degree, so 60 by 2. 90 by 2 is 45 and sine 45 is 1 upon root 2. If you make power 4, you will get 1 by 4 whole divided by 60 by 2, that is 30 degree. Sine 30 is 1 by 2, and if you do power 4 of 1 by 2, you get 1 by 16. N1 is given 20. So 20 upon N2 equals 16 by 4. Gets you 4 directly. So therefore N2 equals 20 by 4 and 5. So the answer will be 5, and we will go with option number 3, which is absolutely correct.